I'm Andy Charniello. I'm the head coach of the Big Squad. We've got Adam Poole, Tom Bruns, Charlie Taylor with us today. Full disclosure, not a controls person. I pretend to be a controls person. I'm kind of here to, one, give you some context, and two, I'm going to represent a little bit sort of the end user side of things. I'm also our drive coach. So I was the one that was working with this system when we were on the field, that kind of a thing. So I'm here to answer questions about that as well. What we're going to be talking about today is our process of our first attempts at vision processing. I'll give you an introduction to the team, a little bit of team history, some context, talk about how we used vision for last year's game, and then talk about what things went well, what things didn't go well, and give you a look into the future where we're headed from here in terms of vision processing. What we want you to get out of this presentation is an understanding of what are the elements that go into doing vision processing, and to really come away with an ability to assess if you're ready to go into vision processing or not, and when is the right time to take that dive. It was a significant investment from us from a time perspective to do it. So we want to help you to make that decision. So I'm going to start you off with a little bit of an understanding of where we came from and where we've gotten to. So I'm going to give you a history of this team in terms of machines, robots. And our first season was 2012. This was our robot for that year. Shot basketballs. It was a rookie robot. And we were very excited when it moved and got the basketballs out of the robot. You might be surprised to know that we did indeed win the Boilermaker Regional and advance to World Championships. We did that quite literally on the backs of our alliance mates. We did so the end game was doing a triple balance for big points, 1501. Basically had a flight deck for us to land up, so that was how we did the triple balance there, which was crazy. But I want to talk about each of these games in terms of vision. We obviously did not use any vision that season because our basketballs did not exit the robot in any sort of repeatable manner. When they did exit the robot, they had forward spin because we understand basketball. So they didn't actually make it into the hoops. But this was a game where vision processing was a big deal. You know, we have a small goal relative to the size of the game piece, and there were reflective targets right at each goal. So it was a game where vision processing may have been the right choice for a team that had that capability. The next year we had the Frisbee games. This robot was called Discobolus. It got renamed by the announcers Disco Bobulus. And so this game, again, did not choose vision processing. Maybe if you're going for the high goal, it was worth doing, but the method that we chose instead was to be a sweet spot shooter. And so we found we would literally touch up against the backside of the pyramid, and we had the robot at the right angle, and then we would hit the target every time. So step one of that was having a repeatable shooter.
Just want to point out,
Yeah.
notice the effect of the flash on the targets there. That'll be important later.
Okay, 2014, shooting the big balls. With our surgical tubing powered launcher, we have real issues with reliability and repeatability of launch speed. So when we were shooting in autonomous, sometimes we would hit it and sometimes we just wouldn't. So if we had chosen to do vision processing, I don't know that it would have helped us really, because we couldn't get the ball to leave the robot the same way every time. We struggled with that whole season. It's very frustrating. 2015, vision processing. There were little reflective things on the yellow totes for the autonomous mode. I don't know that teams used those to great effect in any way. We were, stacking totes. So not much of a vision processing year there. But if you notice from the progression of the machines, we're starting to have more and more machine components. We're getting some more experienced team members, some better engineering support. This was our first robot that we created in SolidWorks as we were building it, and sort of before we were building it even. So it's a huge new step for us, really greatly increased our capabilities. We saw a lot of success with this robot. And then this previous season's robot, another big jump. We did, this is our first time that we put the resources into a custom chassis. We had really great machining support with laser cutting, that kind of a thing. And we invested a lot of time in this part of the robot, and making sure that the balls left that shooter the exact same way every time. And that's kind of the secret sauce to the accuracy of this robot, was the fact that the balls left the robot the same way every time. Even with the varying levels of ball compression and sort of the state of the actual game piece, we could get it to be pretty reliable. So that's kind of some context of where we were at the end of this season, but now we're going to kind of take you back to the beginning of the season and our strategy discussions and what we decided we wanted to be. I'll hand that over to Adam.
Thank you. I'm Adam Poole. I'm the other coach for the big squad, the assistant coach, and wanted to talk you through how do we use vision, right? So our strategy from the get-go was really we wanted to be an elite high goal shooter. We wanted more than anything to perform on the shooting side of things, which meant one of the key features we had to develop into the robot was precision. And again, what Andy was talking about, we needed to make sure that when we aimed somewhere, it would go there, right? If we needed to calibrate so that we would adjust where the shot was, as long as it would predictably go in the same spot, we can adjust our aim accordingly, right? So if aiming correctly yields a successful shot a high percentage of the time, that is a necessary component in this system. To make that happen, part of the aiming, how we simplified the aiming process is we added a turret to the top of the robot. That way we didn't have to move the entire chassis and jiggle around every time we wanted to adjust our aim a little bit. It allowed for more precise fine-tuning of that aim. We actually developed two different solutions for targeting, one for Auton and one for teleop. This may be a surprise for you, but in teleop, we were using a camera, but we were not using vision processing in teleop. Okay? We use something we call camera-assisted manual aiming. This is our view of our driver station. This is a 3D printed gun sight. At the end of the target, we have a camera directly looking over it, so there's another point here, line those two up, there's our target. Boom. Okay. Shock is over, sorry.
Our operator was playing a first-person shooter, yes?
Yes. So where was it located? Here was on the robot. The view is directly over the front. The operator's manually targeting the tower. We found, because we did develop a vision targeting system, don't worry, we will get to that. But we found that for our application and the capabilities we had developed by the end of the season, that there wasn't really an advantage to implementing the automatic targeting here, that the operator could do just as well and adapt to other situations. So it was a better choice to go with manual aim here. Okay, so other places we use cameras, really briefly. Boulder Acquisition, right? Visibility, finding boulders on the other side of those defenses was an issue. So we put an in-feed camera in. It's viewing down that way. This is where our in-feed system was. That's a view of the in-feed, so you could see where the balls were even if you couldn't visibly see them from the driver's station. That was streaming again to the driver's station. the operator was able to toggle views between the shooter and the in-feed when they needed to. Scaling the tower at the end, we found that we weren't able to line it up quite right with the gun sights, so we used something we call the kiss cam. That is because if you look right up here, when you close that hook, it kind of looks like an arrow, or excuse me, it looks like a heart arrow, which we called it Cupid, and so the kiss cam was the appropriate camera name for it. Anyway, let you in on the inside joke there. Okay, so the kiss cam is located right by where the arrow is sitting, and we viewed almost directly up at the tower. So the view from it, this is hard to tell, but here's the edge of the tower. Here, there's the target edge there, looking over the release mechanism for the arrow, going right up that way. Okay. So auto-targeting wasn't really an option here. We didn't have the reflective tape that we really relied on to help us see it. I wanted to show you what does Auton look like now before we actually move into how did that work. So we have 4 views here. Let me show you what they are. This is a GoPro on the side. So yes, we have even more cameras mounted on the robot just to record this. But the actual cameras are mounted here. So this looks like it's not aimed properly when it gets there, but it is because it's just kind of pointing off to the side. This is the view that will highlight that what it's actually seeing. It's viewing what the driver would see from targeting it, but is showing a direct aim. So you'll know that it's lined up when it's lined up in this window here. These are just side view and in-feed views so you can see kind of what's going on. All right, so here's what it looks like. They're counting down and go. So we go over the barrier and it's aimed, and now it's aimed centrally. Spin up and boom. All right. I'll back it up and let you see it one more time just in case. And you get this loud spinning sound in the actual audio here. I guess it's not coming through. That's okay. And we're lined up now, and boom, buckets.
I want to put a quick side note in.
Okay.
This is just sort of vaguely off topic, but in that top left-hand view, you see our driver station. There's a lot of data updating. We used that really heavily. That was a GoPro mounted on our driver station to record the screen. We used that a lot for troubleshooting and figuring out, if we missed a shot, why did we miss the shot? So we were going for that sort of extreme level of accuracy. So we had to figure out, so what were the settings that led to the missed shot? So that was one of the ways that we captured data.
So this is the data you're talking about. We could go back and see what is it seeing, what feedback is it giving us at the moment that something went wrong.
Yeah, so and that biggest number there is the error, which will come in later.
Yes. Okay.
In degrees. In degrees.
Yeah. Any question, or how many cameras did you guys have, like, on your?
More?
Hooked up to the control system.
So the driver or operator we're using, there were 3 different views they could choose between. Then there was this 4th one, which is the infrared camera we used for the actual vision processing. We were not using the same one as the driver. It was just located in almost exactly the same spot. Here's, to give you an idea, here's the shooter camera up close, and there's the infrared camera directly above it. And that's an IR LED, which we'll get into later.
And we have the GoPro.
We have, yeah, any GoPros were just for recording things. Yes, sir, in that.
One of the issues that our team has run into with cameras is bandwidth problems. And I am assuming with so many cameras, if one is activated, all the others are not.
Right, we're
So
only
that-
streaming one at a time.
Okay, so that eliminates the bandwidth problem entirely.
That's why we had shot view toggling between the ones. The infrared camera never goes to the driver's station. It stays on board. So we'll address that. That's a really important point to make.
We also had left and right camera.
We did try left and right. Did we ever use them in competition? I don't think we did, right?
Yeah.
We were experimenting with, can we see even more view out here? But at some point we say, okay, enough cameras. We already have a significant share of Microsoft Live cams in the country. All right. So that's the view.
One we'll add is that out of box, if you're a Java developer, the out of box PDP libraries don't support more than one camera, but there are some community extensions that can replace the out-of-box class, let you do switching between mobile cameras. Not that hard.
Okay, this is the view that our robot had when it was doing vision processing, right? That green line is not actually what the robot's looking at. That is something that we put on the screen to show center line of the image, okay? Because we knew that we had aligned the camera and the robot head at the very center of the image. So what you see down here is actually the top of the gun sights. Not the same exact view as the driver, but pretty close, right? It's lined up the same so that when it's on target, center of the image, center of the target, center of the robot. Buckets. Okay. So we were doing vision processing using software called RoboRealm, which we will get into that in a bit. Auto-targeting, I just pointed the center line there, yeah. Infrared camera, RoboRealm, and turret working together. So the turret uses an encoder to know roughly where it is, but the important feedback in the end for aiming it is that error value that we'll talk about in a bit, passing that into the RoboRio and have it respond appropriately. So the message here is the thing that you want to be passing the RoboRio, at least for us, we found it to be very important to keep that data simple, right? You want a simple thing to respond to in RoboRio. You don't want to have to do all of this extra processing work because anytime you're doing that, it's off doing vision processing instead of doing other stuff, and you don't want to take up processing power with that. That's a simple way to explain it, I guess. Okay, brief story. Actually, I have to read this one because I wrote it down and I like the way I wrote it. Sorry. If you've tried to program Auton before, you've been here. You have some task you need the robot to do, but how do you get the robot to know when to move from one step to the next? It's really challenging, right? We had a great mentor a couple of years ago who was really good for our team, but he just didn't get control issues. I remember one time we were discussing Auton for Recycle Rush, right, with the totes. And without getting into the details of the challenge, I'll give you an idea of how it went. We were standing there talking about the robot and how to move, how it had to move for Auton. And he comes behind the robot and takes it and he says, just make it do this. And he moves it over, right, like an OG type of shape or a parallel parking maneuver. And I'm thinking, okay, so when does the robot have to, like, how does it know when to start turning? How does it know when to stop turning? How does it know when it's aligned properly? The thing that I was trying to describe to him at the time, unsuccessfully, is this closed loop feedback. What happened there? Let's go down. Closed loop feedback for image processing. So this is how it works. You have your infrared camera. It produces a raw image. Pass that into RoboRealm. All right, we're running RoboRealm on a separate coprocessor, which Charlie will describe. We process this image pipeline, which I will walk you through later. It sends just target coordinates, the 4 important points for where that target is located in the image. Sends that to the TCP socket server, which calculates the error value, which then passes it to RoboRio. RoboRio says, oh, you just got this error value. If you have a negative error, turn left. If you have a positive error, turn right. So give a turn command to the turret. The turret actually adjusts the aim so the infrared camera sees something different, and you work to reduce that error value until it's within your threshold. That's the whole overview in a nutshell. So I'm going to pass it over to Charlie at this point to talk us through the journey that we went through to kind of develop this. Thank you.
Thank you. Hi, I'm Charlie Taylor. Been a mentor on this team for 3 or 4 years. 4 years, thank you. I did some of the work on the infrared system, and looking forward to telling you about it. Does this work? No, it didn't work.
Yeah. What's the mute screen on this here?
That phone. Okay, so, we started off January 3rd or 4th, whenever build season started, and we sort of sat down and outlined what our goals were for this robot given the game. And we, basically shot for the stars with the idea that if we failed, we may land on the moon. And so we envisioned early on developing a robot that could identify the target. It would dynamically aim at the target and then lock onto the target while we're moving across the field, notify the controller and then or the operator, and then he could fire when he was ready. So that's sort of our grandiose goal for the robot. Fortunately, as part of our strategy, we recognized that the developing vision was going to be a really long journey. And so we consciously developed the infrared targeting system as a separate component that we could plug into the control system. And at the same time, we developed this teleop shooting strategy where we basically had, as Adam was showing you, the camera-assisted manual aiming. So the operator was manually aiming using the camera. That was supposed to be an interim solution. So our initial work on our infrared targeting system started by, I did some Google searching and came up with this paper. Let's see, look at that. How 987 used a Connect. And this basically went through how they used a Connect connected to a Panda board running C++ for the Rebound Rumble game in 2012. This kind of gave us a foundation to start with. I also did some additional searching and came up with this software, RoboRealm, which is a nice GUI-based image processing system that runs in a Windows platform. And one of the nice things I discovered is that the license is included in the kit of parts. So we started off with some assumptions early on, and we thought that an effective IR vision targeting system, that we call an IR BTS for short, would require two things. First of all, it would require us to locate the horizontal center of the target. So if you're thinking about the target being here, and we would have to rotate the turret towards the center of the target. And this would be done by calculating the degrees of rotation that were needed. This turned out to be a really easy calculation. We also assumed that we would have to estimate the distance between the robot and the target in order to align our trajectory. This turned out to be quite a challenge. It really required some fairly gnarly trig and geometry calculations. And the other thing we found out is that the accuracy of this estimate was dependent upon the resolution of your camera. So the Connect that we started with was only 640 by 320, I think it was, right? Or yeah, something like that. Pretty low resolution. So it didn't give us very good estimates. Later on, we got better ones. We also assumed that the IR BTS would be as effective as our camera-assisted manual aiming system. So we thought we could, we would even better our game if we developed the IR system for the teleop. As Adam said, didn't work out that way. So luckily we got some breaks. Reality drove some simplifications. We found out that we really did not need to estimate the distance. We were very fortunate in that the design of our shooter led to a flat trajectory, which basically eliminated this need. We only had to identify the center of the target. We didn't need to know the distance. And as I just said, CAMA proved to be just as effective as the IR system. So we were, we could just narrow in for an Auton system.
Charlie, can I interject
Yeah,
here for a
please.
second? Back up on the trajectory thing.
That's not so much a fortunate thing, but something that we look at every year. We want to have the biggest margin of error for getting the object into the goal every year. And so what we try to do is to design our sort of ideal trajectory to be right at the top of the flight path at the goal. So then you've got that big window of the object being high enough to make it into the goal. And so that's something that we started out with this year, which helped us a lot in this process. Then we were less sensitive to how far away we were from the target. Yeah, so.
Thank you. Moving on. But even though we had these breaks, we also had some significant challenges to overcome. The first one is that there's a lot of ancillary sources of IR light, and that can easily distract your robot. So you can get IR light through a window, through overhead lights, through signage along the field, and so we had to figure out ways to minimize the impact. We also had some challenges in terms of how do we have our onboard computer. So we were looking at, we started off with a Surface Pro. How do we have that Surface Pro interact with the Robo-Rio? We were challenged throughout the build season with system stability issues, and we, even in our final competition, we still have a fairly complex robot startup sequence. We've documented it, we need to just go, have the discipline to go through that sequence, because if we take a shortcut, it doesn't work too well. The other thing that we ran into is, so we got our system all developed, and we were ready to add it to the robot, and we found out, gee, we didn't have enough weight allowed to add it on. We were topped out on our weight. So what we ended up having to do is find some substitutes. So for the Surface Pro, we eliminated that and moved our system onto a Kangaroo, which is a small little computer I'll show you in a second. And from the Kinect, we moved to a modified webcam, a C920, it's made by Logitech. You can see the difference in weight. The Kangaroo is like half a pound versus 2 pounds for a Surface Pro. And a webcam is only a few ounces compared to 1.5 pounds for the Kinect. You can see the difference in size. Here's the Kangaroo sitting on top of a Surface. And here's a webcam, the webcam we actually used versus the Kinect. The Kinect has got a lot of metal in it, and it also has some components that we really didn't need. It had a vision cam as well as a IR projector.
Didn't they also outlaw the Kinect on the robot? Because they had motors in it?
Is it literal?
Oh,
Yeah. Yeah, if you look here.
It's not a simple process to take that motor out.
Yeah,
Yeah, I don't know why they took that, why they're enforcing that rule, it's stupid.
So, in the end, we did have some success. However, our IR targeting system was really not ready until very late in the competition season. In fact, in competition 1, we basically were a spy bot shooter. So we parked it right in the corner of the court, manually aimed it. Andy manually aimed it at the target, and in odd time we would launch a ball into the target. In the second competition, we chose to drive across the outer works into the courtyard, but did not shoot. In the third competition, this is where this actually was at Worlds. We were able to drive into the courtyard and then shoot with the infrared system. So in the end, the IR VTS proved to be very effective, both at the Worlds and that competition we had in September. So why were we successful? I think there's 3 main reasons. First of all, our robot design really simplified what was needed. Our shooting mechanism is, Adam was saying, and I think it was Adam, was very repeatable. 90% of the time we would get, or maybe even more, we would get the ball into the target. The trajectory required very little adjustment over the range of distances, so we didn't have to measure the distance. We did have an adjustment built into, or the adjustment capability built into the design of the robot, but it wasn't used very much. And so aiming was only a function of rotating the turret. The infrared system, we developed it as an independent subsystem. That really helped, so that when we were ready, we could plug it in. Or if we had trouble with it, we could also unplug it. So, and then the other thing that was really helpful is we were very fortunate to be able to build a nearly identical practice bot. And so this allowed us to develop our Auton strategy as well as our code and our vision system well into the competition season. At this point, we're going to switch gears a little bit and talk more specific about the vision system, the IR vision system. You'll see this diagram a few times. I am going to talk about the webcam, basically the hardware, the webcam, the kangaroo, and am I missing something on here? I guess I'm not. With the webcam, I'll also talk about the IR light. So, in total, the hardware that it took for this was less than or equal to 1 pound. So let me talk about the webcam. So a standard webcam, and we use the Logitech C920, each pixel is made up of a red, green, and blue sensor. Fortunately, the red sensors not only pick up red light, but they also pick up infrared light. And what manufacturers do is they put a filter in, which is in this slide. So this is my thumb and my forefinger here holding this little filter that blocks the IR light but allows visible light to pass through. So we were able to create an infrared camera by simply replacing this, this filter with an infrared filter that basically, this allows IR light to pass but blocks visible light. So in this case, I'm actually holding this filter material up to a very bright halogen light. As you can see, light's passing through my finger but not through the filter. There's tons of websites out there that talk about how to do this. This is just one of them. But one of the things I want to point out, excuse me, my mouse drying out here, is all of these instructions talk about using like a piece of developed exposed film, photographic film, as an infrared filter, or for those of you who are old enough, a piece of floppy disk that you can stick in there.
Where do you find that?
Yeah. Actually, I had a whole stack of them.
Back of the desk.
Yeah, the back of the desk drawers. But what I found, or we found actually, is a better solution is actually to buy IR filter material. And this is the only one that I was able to locate. It was sold by B&H Photo. You can actually go on to Amazon and buy it through Amazon. And it's this material right here.
I got a question.
Yeah.
What infrared?
Well, I think infrared has, first of all, I guess the first answer is we saw somebody else that was doing infrared. It worked. It was based on the Kinect. And so we just sort of went down that route.
Like, do you notice fewer like noise sources of infrared, or is it?
Well, I'll tell you, we didn't try visible light, but my guess is that we have filters that just filter in on the IR light, as opposed to you're not having to worry about different colors mixture of colors, that type of thing. So, some teams do use visible light. You see them with like the green ring or the blue ring around the camera, right? But we chose the IR light because we started off using the Kinect. And the Kinect actually has that IR projector that, in the way the Kinect works, is it sends out a matrix of infrared light, and then it looks at how that matrix is distorted. And what you do to use the Kinect is you basically put some kind of like translucent material over the IR projector to kind of wash out the matrix and spread the light.
One thing, past this section, none of the rest of the solution really depends on the fact that it's IR.
Right, yeah, I was just curious, because it seems like a solution that not a lot of teams do, so I thought, maybe there's a real specific reason to it. That you guys are on. Yeah, okay. All right. I mean, you might have less like image processing, like filtering new colors, so that might be a step that you should remove from the
It's kind of a mechanical approach to the filtering,
Right.
right? With
Oh,
sticks and-
I definitely
sticks and
prefer
floppy
like a
disk in front of
physical,
it,
yeah.
instead of having to do as much in
Yes.
software. I think
Right.
that the
Hardware is always fast, almost always faster than the software system.
the consequence of it is that we ran into lots of times where we weren't actually able to practice because the environment we would be in, practice in this room, for example, because of not incandescent, but fluorescent lights.
So we had to work through that, but we found ways to do it.
You'll see all the top teams are using color and doing advanced
Right.
filtering of colors for that reason.
So, I mean, what happens if like you're at like some event where there's like a bunch of windows in the background or something like that? Is that?
Yeah,
is that
Adam will
You're
get
gonna
into
talk about
that.
robo and both.
I'll
Okay,
walk you
all right.
through the pipeline,
right.
so, yeah.
So, one of the challenges here, as you were just asking or alluding to, is that, the ambient light does cause us problems. So one of our resolutions was to bathe the target in IR light. And to do that, we used this little LED, pumps out a lot of infrared light, which of course you can't see unless you're looking through a camera, but so we have this IR LED. It's mounted to a piece of aluminum for a heat sink. If you don't do that, it'll burn out really fast. And then this is hooked up to a constant current puck. And one of the other things that was really critical is the placement of this LED. In fact, one of the things we tried at one point was to mount it alongside, point over here, a little bit further away from the camera lens, which is here, and it made a dramatic difference. So one of the things I would advise if you go down this route is spend a little time figuring out what is your optimal placement of the LED relative to the camera. At this point, I think, no,
Kangaroo.
yeah, that slide messed me up a little here, I'm sorry. So now I want to talk about the Kangaroo, which, as I mentioned, was running Windows 10. It was our replacement for the Surface Pro, because the Surface Pro was too heavy. The Kangaroo is very nice in certain respects. First of all, it has a self-contained battery. It's powered with 12 volt, so that just plugged right into the VRM to keep that battery charged. We hooked it up to the Robo Rio by Ethernet, just running a cable through the radio. And then finally, one of the challenges with the Kangaroo is it does not have a keyboard or a monitor. And so we chose to use a mini keyboard that's about this big and a monitor that's about this big. It worked, but you have to have really good eyesight. When you get young people to look at it and not people over 50. I think at this point, I'll turn it over to Adam.
So I'm going to walk you through the pipeline, but as we were mentioning before, the pipeline is at the beginning, at least, contingent on using IR. What I mean is, you'll see that these are the two targets and the sites. So it's hard to tell here, but that's the tower. That's because we blocked out most of the visible light. All right, all you're seeing is infrared, and the reason that these things pop the most is because of that LED that we have. Okay, so in RoboRealm, and this isn't going to serve as a total tutorial on how to do this, but I am happy to answer any questions afterwards. In RoboRealm, you have an image pipeline. Okay, so you start with an image. See, I say display that center line ahead of that. Then here's the input of that camera, the C920, and the first thing we do is we filter out so that almost nothing is visible, and it's really hard to tell here, but the targets are still visible, but almost everything is not, right? Then we go into a blob filter, which this blob filter in particular looks at anything that is still there and is larger than just a few pixels, so that now what we're looking at is something that is binary. It's either there or it's not there. There's no brightness, there's no color, and once you get to this point, the processing is the same whether you're using color or infrared or whatever. You've got an image where you've got to find the shape, right? Okay, so how do we find the shape? Well, first thing we do is we smooth the hull, meaning anything that has kind of a jagged edge, it doesn't look a whole lot smoother, but it is. If you zoom in on it, the pixels get kind of strung together. And then we do a convex hull move, which is really important. That takes all the outer parts and connects them to make anything that's concave a filled-in object. All right? To the robot at this point, it's seeing 5 things. It's seeing this blob, this blob, this blob, this blob, and this blob. And it doesn't know which one you want to talk about. It doesn't know which one is the most important. So the way you tell it that is, and unfortunately this isn't broken down in the way that it works, but I'll talk you through what 3 things it does. First, it looks for the largest 3 things. So it would filter out these 2, right? It would see this, this, and this. Then it looks for the uppermost of these. Okay? So it takes the 2 that are uppermost. Okay? So now I probably have 2 targets in my view. And I want to pick, in this case, this one we're running right here is the rightmost. Okay? We had one that was centermost of the image, rightmost of the image, leftmost of the image, depending on which defense we passed. So, in this case, we select the rightmost, and it filters down to just the one blob that is the rightmost. You can look for things like the shape of a rectangle and other things. There are lots and lots of options, as you can see, for the filters. It would take days to go through them all, and I'm not an expert in all of them. The last thing we do, which was crucial to the success, right? I said we broadcast very simple pieces of information. We don't broadcast this whole image. We broadcast the coordinates of these 4 points within the image. Okay? The X and Y values for this point, this point, this point, and this point to the next part of the to the process, the vision. What do we call it? Disaster. Yeah. Okay. So I actually put those in there twice. So I was going to talk you through that.
Can I just go back to one thing, the
Yes.
last slide?
This one.
One of the key things we're going to hit on is the camera placement was key. It was located on the turret, looking directly where the shooter was aiming. So the center of the field of view of this image is always exactly where we're going to shoot. So the key problem is only, how do you get the center of the image you found in the center of the field of view? If you can do that, you're directly aligned.
Why, you may want to mention why we chose, leftmost, rightmost.
Yeah, because of the different positions, we knew that from the perspective, when we would go over a defense, then we would have a couple of targets in view, and although most of the time we might be able to make it in either one, we selected the optimal one, so we know that from this position, the rightmost one is the one that's going to be the better target, rather than make it like select based on the area of the image, which is possible in RoboRealm. We just said, hey, pick the one that's farthest to the right. Simplify the problem.
And to the discussion of the visible light versus IR, you can make RoboRealm select a certain wavelength. So if you've got an LED that's putting out a certain wavelength, you can select on that, and we just chose a wavelength that's IR.
Right, so that would happen right up here. You filter for a certain color and say nothing else, ignore everything else. to the point of windows and other problems with IR light, you can crop the image. So in certain environments, we would actually have to go in and modify the pipeline once we had seen what is just the infrared light, what are the sources of infrared light there. And so we might, if we had windows up there, we'd crop the image. We still knew that we'd see what we needed to see, you know. You kind of got to adjust this pipeline based on that context and based on what cameras you're using, yeah.
How quickly could you get through the pipeline as far as once you've gotten that input and then get into that 4-point output? And I guess how dependent of how many filters did that kind of, how much was that?
Are you asking about how fast the computer executes it?
Yeah, the whole image processing kind of chunk of your loop for your closed feedback, how long does that take?
We could do 10 to 20 scans per second.
And Tom, you'll address that a little bit, where you gotta wait for the one signal so that the timing works out.
So that first image you showed here in RoboRealm, that was, you said, without any filtering, that first one?
That's an infrared image, well, sorry, the lines I put on there, the orange lines, just to show things.
Yeah, just superimposed. But that is remarkably little, I would think. So that's like, what environment is that? I'm curious.
That is in our commons area at school with, the windows are back behind me. So it's a Saturday, so the lights are off.
So
But
there's no
most lights, like, I don't know that these would produce IR, but some halogen or fluorescent ones do produce IR. Normal incandescent bulbs do not.
Yeah.
So depending on what lights you're dealing with, you've got more to work out.
So remember the first row of image is already cleaned up quite a bit from
Right.
the physical filter.
Yeah.
Well, the other thing, yeah, you can filter out, like, you can chop the top off your picture, right?
Here, let me see if I can go back, I can actually show you what that image is. Or one very much like it. There you go.
Yeah.
See, so there's lots going on here. There is a light on, but it's being filtered out. That's,
Did you chop the top?
I did not crop it, it was just like that, it filtered that out. Okay.
So one of the things we found was you could, if we had problems with lights, overhead lights, that you could essentially crop them out of your image before you do this exercise here of identifying the four corners.
In the interest of time, I know there are more questions on this, and I'm happy to talk to any of you about either RoboRealm or filtering in general, but I want to make sure we get you the rest of the information, so I'm going to hand it over to Tom now to talk about how the TCP socket works.
So when we first started on this journey, we expected that we were going to do a distance calculation from the target, which our initial work Charlie did less than believe that was going to be a really complicated calculation. And we decided not to put that on the RoboRio. So we were going to have some kind of Windows PC on the robot anyway to post RoboRealm. So we had this image data server, which is basically another program we wrote that ran on the Kangaroo. It did a TCP connection to RoboRealm, reading data through its API, did some calculations, and then supplied that. It basically sat as a socket server that we could talk to from the RoboRio. It had three main functions. One was this client, which talked to RoboRealm and pulled those 4 points back as fast as it could read them. Two, do a calculation, one up being a relatively simple calculation that we're going to talk about. And three, exposed a socket so that this is the RoboRio, it could read data during its scan cycle. Okay? Here's kind of the guts of what really is going on. Think about this logically being that same picture Adam was showing you a minute ago. Think of the white as the field of view. Logically, here is the target, and the thing we're getting back is those 4 points. There are some things we know about the image that we get from RoboRealm. We know that the field of view is a fixed size in pixels, so the coordinates I get are relative to a fixed field of view. we know that the field of view is also a fixed size in degrees. Very important to us, okay? So what we're going to ultimately come to is figure out this offset in pixels. And there's really 4 simple calculations. One, we figured out the center line of the field of view, which is a calculation based on the total field of view width divided by 2. We then figured out the center line of the image. So knowing these 4 points, we figured out where that was at. Then we figured out this distance. Then the angular adjustment to get that in line with that is really just what portion of this field of view in degrees was that distance. Wound up being just this relatively simple calculation. Key thing is, our camera field of view is always centered on exactly where the shooter's going to aim. So the whole goal was to drive this and that angular number to 0. That, if you remember the feedback loop that Adam was talking about, what this did is fed back an angular, an offset angle. Here's the air angle you have to adjust for. That got fed to the Robo Rio, which in the Aton code made an adjustment, and it kept this closed loop cycle about driving that air to 0, and if it was within a threshold, then we fired. Any questions about this? Now we're going to jump down to what happened on the Robo Rio itself. In Aton, if you're familiar with that, we had a 5-state state machine in Aton. The first one was drive across defense. So we have to get across the defense, which for us was relatively simple. It was just for a given throttle percentage for a given period of time. That number may have been different based on what defenses we were going across. It was pre-programmed. We had the benefit of the fact that the robot was relatively consistent. If it crossed over, it wound up well within our tolerable range for the shooter. So we didn't have to worry about if we went a foot forward or a foot less. Our shooter was fine with the trajectory. But to give ourselves the most advantage, we said we always want to be sure that we get across the defense, that the target is somewhere in the field of view of the camera. Because if that square, which makes up the target, is not completely visible, then the RoboRealm is not going to be able to figure out that it's out there. What that led us to is, hey, we know from a number of tests, we can do we call the rough adjustment. Just turn to a general angle based on what position of the defenses I was going across. If I was going across on the far left defense, turn that way a little bit. Just enough so that somewhere in the field of view we're going to find the image. That's what this rough adjustment was. Once we got across the defense, we just did a fixed go to this angle. And it was a different angle based on whether we were 1 through 5, but that just made sure we were in the field of view. Then we started reading the vision data server. And we had a course adjustment speed, which was, let's just get us relatively close to being lined up. This was just this iterative feedback loop. Then we jumped into a fine adjustment speed, and when a slower speed, when we got within our shoot threshold, then we'd spin up our shooter wheels and shoot the ball. And that was what you saw going on in the video that Adam showed you at the beginning, where we crossed the defense, it turned, then turned some more, and then fired. For us, the controls team, the moment of angst was in Aton. As soon as we heard the wheels spin up, then we knew it was going to shoot the ball. We knew it had found the target, and we were going to set the basket. Our real goal on the controls team was how are we going to add value by adding points to this team? And by adding points, it was a 20-point Aton. And the only way we were going to get a 20-point Aton was to be able to do this shooting. The path we chose is not the only path. This is not all probably the possible options, but it's the options that we're aware of. And really, the first decision comes down to where are you going to run your vision software? The options we were aware of is some people run it on coprocessors on the robot. That's the path we chose. Some people run it on the Robo Rio, and there are actually even some teams that are running it on the driver station, believe it or not.
Oh.
Yeah. Here are some of the vision software options that we are aware of. Which one is available is a lot dependent on what platform you're choosing. So if you want to use RoboRealm, because you like that tool, then you're going to have to either run a Windows onboard coprocessor robot or do it on the driver station. RoboRealm doesn't run on the Robo Rio. Grip, that's probably another option. Saying, isn't all of them, so we'll, okay? Some of the main ones, RoboRealm, OpenCV, Grip are three of the main options that we're aware of. There probably are others.
We ran grip on a Kangaroo.
Great. Okay. The two main ways you can talk, if you're not on the RoboRio itself, the two options we're aware of are you can do socket communication or you can do network tables. We'll talk some more about that. Network tables is a native protocol that the robot uses itself to talk to the driver station. RoboRealm actually has built-in support for talking at network tables. We didn't choose that because we had that separate process running on the computer. We'll talk about that. We'd be concerned about people who choose this option only because of the potential latency issues, and it's pretty hard to get the image showing up in the dashboard camera into RoboRealm to process it. People who've seen have done some kind of neat fancy screen capture approaches. But doing it on the robot seems to be a more robust and performant way to do it. What we described today was very much an alpha beta kind of approach for us. I mean, this is our first season doing it. A lot of challenges and things we overcame. We wound up with something which, when we were careful, we could be successful with. But it's not, it was just a great starting effort for us. What we're talking about here is, what are the things we're working on right now for next season? The areas we want to improve on. The two main goals that the team gave us. Number one, we learned that we had a complex startup sequence, mostly because we had these two computers that had to make a socket connection when the robot started up, and if the radio was on or not on before the Kangaroo came up, it was tough. You had to sequence it very carefully. All right. So the first thing we want to do is decrease or eliminate that sequence complexity. Two, the idea that we learned that, hey, as Adam talked about, we had three different RoboRealm programs. We had a left one, a center one, and a right one. And we didn't have enough time in last year's season to make that easily automatically selectable. They were before a match going using the little keyboard, little monitor to say, oh, we're in position one, let's go pick the left program. Okay? It's crazy, all right? So if you look at the things that we're focusing on, number one, we're going to go look at some of these other platforms and see, do we see any of them lead us to a better solution for the team? Two, we decided we can get rid of this vision data server component because we've come up with the fact that the calculations may not just be all that complicated. We can take the raw points, you saw the math we did to figure out the adjustment angle. It just wasn't that big a deal. We could do that math on the RoboRio. Three, we evaluate using RoboRealm's out-of-box network table support. See, that's a more robust way than using the TCP sockets. There's less code involved. Four, RoboRealm's API lets you dynamically, on the fly, swap which pipeline program we're using. We already have in Auton dashboard choosers that startup we tell it where the robot's at so it knows what Auton program to use. We could just as easily swap which pipeline programs are being run and eliminate a lot of this stuff. I talked more about this power up. You know, we traced the power up sequence problem to being tied to we had a USB dongle in the Kangaroo, and if the radio wasn't on when the Kangaroo came up and it couldn't get an Ethernet connection, you need to drop the radio up later. It's kind of a pain in the butt. But trying to solve all those problems. If out of this combination of things, our belief is if we can deliver both those advantages to the team, then Vision becomes a much more operationally friendly solution to the drive team. That's really what the goal is. Reduce the complexity for them pre-match.
So is your team ready for vision processing? This is what some of you are wondering right now. What it came down to for us was, does your robot perform reliably and repeatedly in teleop? Anything that you want the robot to do automatically, it's got to be, it's harder to make it do it automatically than it is to get a human to do it, right? There's less adaptability in there. Is there any other lower hanging fruit that might provide more benefit to the team? So have you kind of reached those other pieces of the game that may benefit more in that year? Do you have team resources, that is students and mentors and time and money to devote to focusing on this issue. And I do mean focus because if you're working on this, you're probably not going to be able to split your time between vision processing and, writing the main robot sequence code. And do you have a high degree of confidence that you can develop a solution to each of the pieces of the puzzle? So these are the pieces of the puzzle. In a hardware sense, you got to provide a usable image. You got to have some sort of processing place, so we call it a coprocessor, right? And you have to have a robot design that provides for repeatability. From a software perspective, you have to have image processing. You have to have a method for passing that data to the RoboRio, and you have to have some module on the RoboRio that can respond appropriately to the data. If you can approach those 6 things with a high degree of confidence, then yeah, you're ready. Even if you're not ready, using the solution we talked about for our teleop, where you just have computer-assisted manual aiming, that is a lot simpler and does not require the coprocessor. Tom, what were you going to say, sorry? Okay. Cool. That is the end of what we have to say to you, unless you have things to ask of us.
Okay, from an idea of research, design, programming, implementation, and testing, how much did you guys do and how much did your students actually do?
Good question. We have a relatively small controls team, and so our lead programmer was focused on, the student lead programmer, I should say, was focused on developing the main robot code so that we could go over and learn how is this actually done, because none of us had done it before. So we spent more time on this, they spent more time on the main robot code, if that answers your question.
How did you reduce camera shake when the shooter was on?
Once we were lined up, we didn't have to worry about shake. So, right, we didn't spin the wheels up until we were aligned. Our image was stable during that point, lined up, then kick the wheels on, and we already know we're in position to shoot. So, good question.
There's also, the turret was a relatively robust mechanical thing. I mean, I think even when it was on, we saw some shake, but it was not enough that was taking us off target.
That's true.
And our threshold was plus or minus 1 degree, right?
Yeah.
So that shake wouldn't have taken us outside of that threshold.
What method did you guys use to actually connect all these cameras here to the reel?
USB.
So they're all USB cameras to a home?
Yeah.
I mean, you like us may think, gosh, a radio with only two Ethernet ports, you're either going to go to a hub to get more Ethernet ports, or you're going to use a USB hub to get more USB ports. One way or the other, you're going to do that. The RoboRio itself has no problem having 2 USB cameras plugged into it at the same time. It's just you have to have the software to switch between reading them, that's all.
Yeah, so what software do you guys use for that?
So honestly, there's another team who published a replacement for the out-of-the-box camera server module that really had like 10 lines of code difference just to let you switch the cameras. Well, I suspect that's probably going to be built into 2017 code because the change is so small, and having more than one camera is such a big lift.
You want to mention the camera, I think the problems we had with the.
That was on the Windows side, not on the RoboRio side.
We're using the same cameras that connected to the RoboRio. Were they all the same? Because you mentioned, aside from your aiming, you had one looking at the hooks, one looking at the in-feed, and one looking at the operator aiming.
So we actually had 3 plugged into the RoboRio. They were all 3 the same physical kind of camera.
Okay.
The camera used for targeting was a different camera. It was the Logitech C920.
Yeah. Right.
And that was plugged into the Kangaroo.
Right. What were the other cameras that you used?
Live cams. Or some live cams,
Yeah.
yeah.
Okay.
Worth noting for the mechanical people out there. All the webcams are designed to have flexible mounting so that, you can point them to whatever. I think all of ours at one point were out of their housings, and we 3D printed new housings and mounting situations for all of our cameras so that we could have them rigidly mounted with number 10s and nylocks and all of those good best practices stuff.
Are you willing to publish those?
Yeah, yeah, absolutely. The hard part was the interface with the camera, and we did that once, and then we just kind of added on other things for whatever the mounting solution needed to be.
Yeah, we did similar things, I think, with our camera. We used, what was it, the Axis thing? Which is it's a fine camera, but it's kind of annoying to work with.
And it's expensive to get more of them.
Email me, we'll send them right to you.
Good, thanks.
Well, thank you for your attention and your time.